Okay, first a definition. We're going to say that a graph is acyclic if it contains no cycles or circuits. And we're going to say a graph is a tree if it is acyclic and connected. It turns out in general, we will also sometimes refer to an acyclic graph as being a forest, because the idea is that the connected components of the forest are trees. So a forest is a collection of trees. Finally, a leaf in a graph is going to be defined to be a vertex of degree 1. So the definition comes from the idea that you've got a graph that looks like this, right? So it looks like a tree. And then the vertices of degree 1 are called leaves because, they're the very ends of the tree. Finally, a spanning tree is a spanning subgraph that is also a tree. And these pop up in applications because suppose you have nodes representing a local network and edges with computers that can share with each other, or just some other type of utility in general, then sometimes you have a problem that some path or edge will fail. And so what you want to have happen is that everything still remains connected, which means you want a spanning tree. And so it is a result that every graph has a spanning tree if and only if it is connected. So as long as your network was connected to begin with, you can guarantee that at least one spanning tree exists. And then you'd want to use your resources to make those edges to be the least likely to fail. We're going to prove this result by induction on the number of edges. If there are no edges and you have a connected graph, then your graph consists of only one vertex, and that vertex by itself is a spanning tree. So then, for the inductive step, we're going to assume that for every connected graph on less than k edges, there's a spanning tree, and now we're going to consider a graph that has k edges. Here, k is some positive integer. So as usual for graph theory, this is considered a proof using what's called strong induction, because we're assuming the theorem is true for anything smaller than the case we're interested in. So we see that first we have to consider the case that our graph has no cycles. Then, it is acyclic, and by assumption it's also connected, so it's a tree. And therefore the entire graph is a spanning tree. So just taking the entire vertex and all the edges gives us a spanning tree. So now we have the opposite consideration. Suppose that your graph has a cycle. We'll let x0, x1 through xk be the vertices on the cycle. Then we're going to look at what happens when I take my graph and I remove one of the edges from the cycle. The claim is that this new smaller graph is still connected. It also happens to have fewer edges, so if we can show that, then we can apply induction. So let u and v be arbitrary vertices in the smaller graph. Since our original graph was connected, we know that in our original graph there is a uv path. So a path from u to v. So v0 here is u and vm is v. If the edge we deleted is not on the path, then this path is a uv path in our smaller graph. So this tells us our only concern is if we happen to create a path that actually used this edge at some point. So suppose we had a path that has that edge. So in other words, we've got this vi and vi plus 1 are the edges we deleted. Then the strategy is to take advantage of the fact that that edge was along a cycle. And so just go around the cycle. So that's exactly what we do. We follow v0 to vi, and then instead of going to vi plus 1, we go to the first vertex on the cycle. And then we go around the cycle to the end, and then we go off to vi plus 1. Now, we should be careful And note that even though I drew it so that it looks like the result is a path, for all we know, you could be in some sort of weird situation where your cycle intersects the red path. So all we know for sure is that we found a walk from U to V in the smaller graph. But as discussed previously, if you have a walk between two vertices in a graph, then you have to have a path between them as well. And so now we found a smaller path in G prime. Thus we can conclude, since U and V were arbitrary vertices, that G prime is connected. And since G prime has one fewer edge than G, we can apply the induction hypothesis to conclude that G prime has a spanning tree. Then it turns out that spanning tree must also be a spanning tree of the original graph. So it's worth pointing out this proof could be turned into an algorithm, because what does it say you do? It says you have a connected graph. Does it have a cycle? Yes. Then here's an example of a cycle. Delete one of the edges from the cycle. Okay, are there any cycles left in this new graph? Yes, that one, so delete one of the edges there. And then now that we've deleted two edges, we ask, are there any cycles in the remaining graph? And we see the answer is no, so it means the remaining graph is our spanning tree.